Okay, perfect. All right, so I'm going to be talking about ANOVA and factorial ANOVA using SPSS. So SPSS, you're probably familiar with. It's like the OG of statistical analyses for psychology. Really easy interface. It's point and click. You don't have to use any coding if you don't want, though there is an option to do some coding in the syntax, which I'll show you in a little bit. But the one downside to SPSS is that you have to pay for the program. I've never paid for it myself. I think for graduate school, my department paid for it. And then as an undergrad, they just had it on the library computers. So I don't know what the availability is at UCLA, but I think you should be able to find this for free. Okay, so what we have here is our data set. I just kind of downloaded a practice data set from like some UK university, so it's not the greatest, but it's just good and simple to demonstrate like ANOVA and factorial ANOVA. So here you'd have all your raw data. So if you wanted to open a new one just to show you, you'd go to File, New, and then Data. Also, you'd have File, New, Syntax, and that, I'll just show you what it looks like. This is where you'd enter some of your code, and I'm gonna run this later when we do a factorial ANOVA, because I have some code for interaction effect. I'll close that now. And then, so the raw data is here. When you wanna run a statistical test, you're going to open this thing called output. Let's see, taking a second. Okay, perfect. So here's where you have all the data. When you run a test, everything's going to populate in the output here. If you have, let's say, like different statistical tests you want to run for different hypotheses, you can save them as different outputs. So it's kind of easier to go back and check your work, and it's not just like one big crazy mess. Keeps you more organized. So I like to save different outputs depending on what hypotheses I'm going to be asking. So I'm just going to close this one now because usually it just will populate on itself once you run a test. And here's the data view. So we can see we have our two independent variables, which are going to be group. And in this case, our group is going to be children, adolescents, and adults. So we have 3 levels, and they're going to be coded 1, 2, and 3. And then for sex, we're going to have 2 levels, 0 and 1 for male and female. And then our score is going to be, let's say, an empathy test, and it's going to be a continuous variable. So I'm going to switch over to variable view. And this is kind of where you're going to be doing some of the coding for the variables. So we have all of our names here, group, sex, and score. Something kind of important to look at would be the decimals. So group and sex, we know, are categorical variables. So I don't put any decimals there. Score, however, is continuous. And if we flip back to the data view, there aren't anything in the decimals, but I usually like to add 2 decimal places so I can tell the difference between categorical and continuous variables just by like eyeballing it. So I put that there, but it's totally a stylistic thing. You don't need to include it if you don't have any decimal places. Then for the values, so for group, you're just gonna click here and you can see what we've labeled. So 1 for children, 2 for adolescents, 3 for adults. And you can add, change, or remove everything here, relabel it. This is kind of where you're going to want to control what the names of all the different levels in your independent variable is. Same thing for sex. We have 0 is going to be coded for male and 1 for female. And then we don't have anything for our continuous variable. And then the next kind of important thing would be this. So this is kind of how we categorize our variables. So we know that group and sex are nominal variables. They're categorical. We can also choose ordinal if we had that. So if that was like rank order, if we had a Likert scale, we could use ordinal for that. And then of course we have scale for our continuous variable. So you can play around with this. This is just when you're inputting the data, make sure this is all correct because it's really important. And then switching back to the data view. So what I like to do first is kind of just take a look at my data. I want to eyeball it, look at the means, look at the distribution, look at the standard deviation. I just want to kind of get a sense of what's going on. This can be really smart in case you like mistype something or something's miscoded. You can kind of catch a problem. So always take a look at your data before you run any statistical test, and it will give you kind of a sense of what's going on in the data. So to do that, you're going to go to Analyze, you're going to go to Descriptive Statistics, and then Explore. So this is going to pop up. We're going to put our dependent variable, which was our empathy test score, bring it over to the dependent list, and then we're going to just press Shift, hold down both of our independent variables, and bring it to factor. Then we're going to press statistics, and we're going to make sure that descriptives is highlighted and our confidence interval is 95%, because this corresponds to an alpha level that we typically use in statistics, especially in psychology, at p is less than 0.05. So make sure that this is selected and press continue. Plots, factor levels together, that's good for the box plots. I usually uncheck stem and leaf. I don't find it super helpful, and I'll check histogram instead. And then something super important, so with ANOVA, one of the underlying assumptions is that you have a relatively normal distribution of data. So actually in SPSS, you can have a normality test that will test if at each of the levels of your independent variable, if they deviate from normality or not. So this kind of does all the hard work for you, though I will definitely mention they're extremely sensitive. So I'm going to talk about kind of a rule of thumb if it violates that test going forward, but just check it to see and get a sense of if there's a deviation with one of the tests that they provide. And then press OK. Yeah, and options is good. Make sure that you have both here so we can see our histograms and our statistics, which are just going to be like your mean, median, standard deviation. And then press OK. And then it's going to populate in this new output that's generated. So I would probably save this output as like descriptives or exploratory just before I would run any of the tests. And so here it's going to split it into group, which was our first independent variable, and then sex, which was our second. So when we look at group, we can see our sample sizes. Children is 15, and so are adolescents and adults. So we have a total N of 45, but our sample sizes in this case are all the same, they're equal. And we don't have any cases that are missing. So this is also a good way to catch if maybe you forgot to type something in, and you can go back and look at your missing cases. So really important that you double check this before going forward with any analyses. Okay, so for group, it's gonna break it down looking at each of the 3 levels. So the first level we're gonna start with is children. And we can look at the mean score here, which is 36.13. I kind of want to scroll down, look at the standard deviation, which gives you a sense of the spread of the data, and it's 7.15. So we know there's going to be some considerable variability in children's scores on the empathy test. We can also look at the minimum. So the lowest scoring person got a 22 on the test, and the highest score was a 44, which is a range of 22. This kind of corroborates that we have some variability because we can see there's quite a bit of range in the scores. Skewness and kurtosis I'm going to mention in a second, but I'm just going to do that when we talk about the normality test. So then scrolling to adolescents, we have a mean of 35.87. So comparing it to the child mean, doesn't look like there's going to be that much difference. Of course, we can't say if this is a statistical significant difference or anything, but we can kind of eyeball and say, I don't think these 2 groups are going to differ. Standard deviation is 6.94, so a little bit less, but still considerable variability in the scores. And then we have a minimum of 24, a maximum of 45, and a range of 21. So again, these look pretty comparable. We can't really say if there's any significant difference or not. We can just kind of say, these look like these groups are not going to be differing too much on the empathy test. Going down to adults, however, we see a mean of 48.2. This mean looks a lot higher than 36.87 and then 36.13. So my guess, kind of looking at the data, is I think adults are going to have a significantly higher score on the empathy test compared to adolescents and children, but we have to run the ANOVA to see that for sure. So we can go down, look at the standard deviation. It's 2.40, which means there's less variability. So the scores are going to be more tightly clustered. And we can see that also with our minimum at 45, our maximum at 52, and our range at 7. So again, that kind of corroborates that there's not a lot of variability. It's going to be much tighter. And we can look at that in a box plot, which I think is going to demonstrate that really nicely. Also something to note, this minimum score is the same as the maximum for adolescents. So we know that even the lowest performing adults scored just as high as the highest performing adolescent. So we know that this adults is going to be way above what the adolescents and children are scoring on the test. So then we can scroll down. Here's our test of normality. I tend to use Shapiro-Wilk. This one is good. It's actually a really powerful test of normality. It's good for smaller sample sizes, but it can extend up to like 2,000 or something. And I'd say it's like one of the more reliable and true tests of normality, but it's very sensitive. So we're gonna break it down by each of the levels of our independent variable. We can see for adolescents and adults that it's not statistically significant, which I think this can be kind of counterintuitive, because when we run like a t-test, for example, and we find something statistically significant, it's something that we're really excited about because we found a meaningful difference. But when it comes to normality, if we have a significant result, that means that that level of the independent variable significantly deviates from normality. So it's not something we necessarily want to see. If we have significant results and they really deviate from normality, we cannot run an ANOVA because it's one of the assumptions underlying ANOVA. We can't run any parametric test. We'd have to run a non-parametric test. And I think the equivalent for a one-way ANOVA is the Kruskal-Wallis test if you're going to run a non-parametric. But they say with real data, you're never going to find something that's perfectly normally distributed. It's always going to be a little off. And when you have larger sample sizes, a good rule of thumb is to look at the skewness and kurtosis and see if it falls within the range of -2 and 2. And if it does, it's okay to continue using parametric tests, even though we have a significant result here for the Shapiro-Wilk. So we know that adolescents and adults are okay, but we'll just double check their skewness and kurtosis anyway. And let's go up to children where we found our significant result. So I think Emily mentioned when we were looking at JASP, so skewness is going to look at the asymmetry of your dependent variable with the independent variable level of children. And then kurtosis is the pointiness, so how heavy or how thin it is at the tails. So applying that kind of rule of thumb of -2 and 2 between those values, we see here that this skewness and kurtosis fall within that range. So I would feel pretty confident saying it's okay to use parametric tests to continue with the ANOVA, even though we had that significant result on the Shapiro-Wilk. Adolescents, same thing. It's greater than -2, less than 2, so we're good. Parametric tests, we can do it. And then the same thing here for adults. So I think we feel pretty confident running a one-way ANOVA. Then, so we kind of looked at the data and the descriptives. Now we can see kind of a visual representation of the data. So we have our histogram. This is for children with our mean, standard deviation, and our N. So mean would be right about here. And we can kind of see why this one would significantly deviate from normality. Higher frequency here, lower frequency here. Then we have our histogram for adolescents. Our mean is 37.8 or 35.87. So somewhere around here. And then our histogram for adults, 48.2. Be somewhere around here. Then they have these normal QQ plots, which I tend to look more at the histogram, but you can definitely look and interpret them. So here would be your expected normal value, and these data points are where your observed value. So how it kind of, you can see how it deviated from what you would expect. So here it has the line plotted. Because we have these 2 points deviating from the line towards the lower end, we can tell there's something going on here in the tails. So maybe this one is a little bit more distributed towards the right-hand side. We also see some deviation from the line here. Again, I would just kind of stick to the histograms and then the descriptives up above just to get you, give you a sense of the data. But this is just, if you're more of a visual person and you want to take a look, it's also a nice way of seeing that we have some, variability here in the tails here on the lower end, a little bit here on the top. And then for adults, the same thing, but it's kind of closer to the line. So it's kind of approximating normality a little bit more than we saw in the children. These detrended ones I don't use at all, so I kind of just skip them. And then I go right to the box plot. So just kind of to go over because box plot is kind of confusing. So I just want to break down what you're seeing. This here is going to be our minimum score. This is the maximum score. And we saw those values before in descriptives. Here is your Q1, your first quartile, so the 25th percentile. The black line is the median. It's the 50th percentile. And this top part of the box is your 75th percentile, and it's called the third quartile, or Q3. So here we can see, by far, adults are having a higher median score. We also saw they had a higher mean. But we see much more variability with children and with adolescents, particularly here with children from their minimum to their median, even from their median to their Q1, their first quartile, or 25th percentile. Lots of variability here, less variability from their 50th to their maximum. This one's a little bit more uniform in their variability, if that makes sense. We see it's not, with this one, there's so much more from the 25th to minimum. This one, the median's kind of splitting the variability in half, but still there's more variability overall. So a wider range in scores than we would see for the adults. And for the adults, what's really interesting is that from the median, so the 50th percentile, to the minimum, there's not much variability. The scores are pretty tightly clustered, but we see a little bit more variability here from the 50th percentile to the maximum, so your 99th percentile, and then from the 50th to the 75th. So more range in scores when we get into the upper range of scores, but not as much variability or range in scores when they're scoring a little bit lower. Okay. Anybody have any questions about that? Talking about group? Nope. Okay. So then we can move on to sex. We have 23 males, 22 females, no missing. And then just do the same kind of thing we did before. So we'll look at the means. Our means for males, 38, mean for female, 42. So just eyeballing it, it looks like females are having higher scores on the empathy test than males, but we can't say if this is statistically significant difference yet, just taking a look at it. Standard deviation is 8.84 for males and 7.03 for females. So both have some variability, but a little bit more here for males. The minimum for males is 22, maximum 49 with a range of 27. And for females, 25 is our minimum, 52 is our maximum, and we have the same range at 27. So it looks like even when we look at the minimum and the maximum, they're scoring a little bit higher. We're comparing 25 to 22 and 52 to 49. So it looks like females are doing slightly better. Even the poorest performing female is scoring higher than the poorest performing male. And then we'll come back to skewness and kurtosis, but let's check our Shapiro-Wilk. So for females, not statistically significant. So it doesn't deviate from normality, but it does for males. So let's check our skewness and kurtosis. So it is greater than -2 and less than 2. So it's okay to use a parametric test like ANOVA. And same thing for females, which is what we would expect because we didn't have that significant result for the Shapiro-Wilk. Okay, so getting into the histograms, just to give you a sense, about a mean of 30, I guess it'd be more closer to here, about a mean of 38 here. This is the one that deviated significantly from normality. We can see a higher frequency of scores in the upper range there. And then for females, which did not differ significantly from normality, about a 42.25 here. And then QQ plots, again, we can see what's going on in the tails here and the upper scores and lower scores. And it's trending really closely to the line around the mid scores. And then the same thing. We have a really low score here for females. That's pretty far off from our expected value, but it's pretty close approximation of this line for the observed scores that we saw compared to the black line, which is our expected scores. Skipping these detrended ones, and then let's check the box plot. So we see more variability for males than for females, but what's interesting to note is comparing this median in females to the minimum score, it's quite a range here. When we're looking at this whisker, it's pretty long. Median score is higher than the median score here for males. More variability for males from the median to the minimum point and from the median to the 25th percentile. Pretty comparable variability for their upper range of scores, but I would say overall there's more variability for males, but this does look kind of weird, so keep that in mind. Maybe we have a little bit, it's not an outlier, because if we saw an outlier, there'd be a little circle here, but definitely on the lower end of the scores and pretty far away from where the median is. Okay. So from what we kind of gathered from this, we saw that adults seem to perform better on this empathy test than adolescents and children. And we also saw that females tended to have higher scores than males, or at least that their mean and median were higher than males. So let's go back to our data here. And let's start with just a one-way ANOVA. And one-way ANOVA means that we're just looking at one independent variable. So in this case, we have to use group because sex only has 2 levels, and that would be a t-test, because ANOVA is 3 or more groups. So we can say we have a hypothesis. Let's say we hadn't looked at this, and we're just kind of guessing, okay, what do we think is going to happen? And let's just say we think that adults are going to have significantly higher scores on the empathy test than adolescents and children. That's just our guess, and then we're going to run a one-way ANOVA to see if that's supported or not. So to set up our one-way ANOVA, we're going to go to Analyze, General Linear Model, Univariate. Multivariate is what you would use if you had multiple dependent variables. So that would be like a MANOVA, but we have one dependent variable, so it's univariate. Okay, so our dependent variable is going to be score. That's our empathy test score. And group is going to go into our fixed factors. That's our independent variable. Let me see. So we want to do plots so we can just see like a visual representation of the data after we run our ANOVA. Transfer group to the horizontal axis and add it to plots. I prefer a bar chart, but that's up to you if you'd rather see a line chart. And I want to include error bars. So I'm going to select that as well. And we see it has a confidence interval at 95%. And then we press continue. So it's really important with ANOVA, because we have 3 levels, we have to run a post hoc test if we have a significant finding. So if our F statistic has a p-value less than, p is less than 0.05, we run a post hoc test to see what's going on. So the thing with like t-tests, you have 2 groups. So if you have a significant finding, you don't need to run any kind of additional test to figure out where the difference is. You can just look at the means. And that will tell you which is scoring higher and which group is scoring lower. But we have 3 groups. So a significant finding could mean that only 2 groups differ significantly or all 3 differ significantly. So the post hoc test is going to tell us exactly what's going on. So I'm going to select that, transfer group for post hoc. And then you see this like crazy amount of post hoc tests here. The ones I see the most in research are Bonferroni and Tukey. I'm going to select both just to show you, but you only really need to use one when you're doing it yourself. So Tukey is a true post hoc test. It does all the comparisons. So for all 3 of the groups, it's comparing everything. It's a powerful test. And when you run it, it accounts for all the different comparisons. So it kind of does this kind of behind the scenes math to make sure that we don't increase our chance of a type 1 error, which is basically when we say that we have a statistically significant finding when we really don't. And that's something you really want to avoid in research. Bonferroni, on the other hand, another popular post hoc test, but it doesn't have to be post hoc. In this case, it's definitely more conservative. So it's a little bit better than Tukey at decreasing your chances of a type 1 error. But the flip side of that coin is that it increases your chances of type 2 error. And that's basically saying that you didn't find a statistically significant finding when in error. You just conservative. So one other kind of like side note I want to mention with Bonferroni, and I think we talked about it a little bit when we went over JAS, is that you can use Bonferroni as a post hoc test, but I highly recommend you use Bonferroni in general if you're doing like, let's say, a thesis and you have lots of different statistical tests you're going to run with lots of different hypotheses. So you want to do something called adjusting for multiple comparisons, because if you're running like 10 different statistical tests, you're increasing your chances of getting a type 1 error. So what Bonferroni correction does in general, not necessarily just in post hoc, but when you're doing research, is it accounts for multiple corrections within each, what we would call in research like family or universe. So let's say you had one hypothesis and you were going to run 2 ANOVAs to address that hypothesis. So what Bonferroni does, it's like super simple math. I think Emily kind of mentioned it last time, but our standard significance threshold in psych is going to be p is less than 0.05. But for the family, where we have the 2 ANOVAs asking or addressing one question, you're going to take that 0.05 and you're going to divide it by the number of tests you're going to be running within that family. So it's just 0.05 divided by 2, because we're running 2 ANOVAs. And then you have a new significance threshold in that family at p is less than 0.025. So whenever you run your 2 ANOVAs to answer that hypothesis, make sure that you only report findings that as statistically significant if their p-value is less than 0.025. And then if you had a different one where it's 3, you divide 0.05 by 3 and so on. But definitely account for that if you're running a lot of different statistical tests. It's super important. Okay, so we'll look at both Bonferroni and Tukey, but going forward, you only need to use one. One thing I'll say is these both adjust for multiple comparisons. This is a little more powerful. This is a little more conservative. The findings you're going to get from both are going to be the same direction. So, you know, they're both going to say that the same means differ from the same levels. The only difference between the two is that you might get different values, but the trend is going to be the same. So we're going to press continue, and then we'll go to options. So these are things we want to see populate that we can kind of compare the groups in addition to getting our F statistic. So definitely click descriptive statistics. That's going to just report your mean standard deviation again. Something really important in research and that they're really advocating for more now when we publish work is to report the measure of your effect size. So a significant finding or a statistically significant finding is great, but we don't know if it's a meaningful finding because we need to know the magnitude of the effect. So you could have something that's significant, but if it's a really small effect, it may not be that meaningful what you're reporting. You kind of want to get something with a larger, like medium to large effect. Like that would you almost see with your like naked eye. That's definitely something that would like really make a difference in whatever kind of field of science you're looking at, but really important that we report these effect sizes. One other thing I'm just going to mention, I'm not going to go into it in too much detail, but homogeneity tests are really good and you can run them here in SPSS. So another assumption in addition to normality for ANOVA is also homogeneity of variance. So do we have relatively equal variance between our different groups, our different samples? So SPSS will run that test for you. I'm not going to do it with this data because it's kind of a crappy data set, but definitely run that. If you have a significant finding, it's also not a great sign, kind of like that normality test. So I think you might have to do, it's something called like a Brown-Forsyth test instead of ANOVA. So it's instead of an F statistic, it's an H statistic that you report. But don't worry about that now. But if you want to know, you can definitely check this when you're running your tests. And like super important if you're doing like an honors thesis or whatever, definitely make sure that you have all the assumptions that support your decision to run an ANOVA. But we're just going to stick with these two for now and then press OK. And then we can run our one-way ANOVA. Okay. There we go. Just scroll up. Perfect. So again, we have our different sample sizes, children, adolescents, adults. Here's their means. And here's our standard deviations. So this is exactly what we saw when we were just kind of doing an exploratory look at all the data. Now the test of between subject effects. This is where you're going to find your F statistic. So this is if you're going to determine if your ANOVA was significant or not. And you're going to go right to group here. Scroll across. We see our F statistic is 21.27 and our p-value 0.000 here. So this does not mean that p equals 0.000. If that were the case, that would mean that there's no chance that it could be anything different than these findings, which we know in the world is not true. So that's why we usually set it at 0.05, which means that 5% of the time we'll get a different effect. So just click on this and it will give you the actual number, which is this crazy guy. So for me personally, like stylistically, I would report this at p is less than 0.001 and not this number, but that's up to you or what your professor wants. I haven't seen it reported like this with the E-7 before, but to each his own. So we know this is significant. So the groups are differing. We just don't know which groups or which levels are differing from each other. And then we can look at partial eta squared, which is going to be the measure of our effect size. Now, kind of like, I'm not sure if you guys have learned a little bit about Cohen's d, but there's certain kind of rules of thumb of what is a small effect, medium effect, large effect. So for partial eta squared, it's going to be a small effect at 0.01, medium effect at 0.09, and then a large effect at 0.25. So we have 0.50 here, which is a really large effect. So not only is this finding significant, it's also pretty meaningful. We have a large effect. Okay, so we know that our ANOVA was significant, but we want to know which groups differed significantly from each other. And that's where the post hoc tests come in. So we have this multiple comparisons table that comes up, and we can start with Tukey, HSD, honest significant difference is what it stands for, and we can do our group comparison. So it's going to look at the mean difference between the groups. A negative sign means that the comparison one compared to this has a lower score. And then our significance values are here. So children compared to adolescents, they scored a little bit higher, but it wasn't significant. And that's kind of what we saw when we were looking at the descriptives. The means weren't that different. But children and adults, it looks like there is a significant difference. And children had a lower, significantly lower mean score than adults did. And this little asterisk here, you can follow it to here. So the mean difference is significant at the 0.05 level. So this is what I was talking about when there was like this kind of crazy behind the scenes math that SPSS does for you. And it's adjusting for all the multiple comparisons. So you can take these significance levels at face value. You don't have to do any math adjustments yourself. You can just report it as is. So this would be P is less than 0.001 as your significance for the children versus adults. So children versus adolescents, it's just the inverse of this one. They've just been flipped, and we know it's not significant. Let me just move that. And now we can look at adolescents versus adults. Again, we have a significant difference here. P is less than 0.001. Adolescents are performing worse. They have a significantly lower mean on the empathy test than adults. And this is probably the easiest way to phrase it. So we can say that adults had a significantly higher mean score on the empathy test than children, and you can report the means, and than adolescents, and report the means again, and you could say P is less than 0.001. Okay, so we know that adults are differing from children and adolescents. That would be our main finding, and that's what you'd want to report for your ANOVA. So you'd first report your F statistic, and then report your findings here. Bonferroni, just to kind of do the comparison of the two different post-hoc tests, in this case, it's actually the exact same numbers. Oftentimes it's different numbers, but again, you would always find the same trend. So whatever test you do, adults would always have a significantly higher mean score than children and adolescents. But this is just to give you a demonstration that you could use either one, basically. Okay. Does anyone have any questions about that? Here are the means plotted for one-way ANOVA. Nope? Okay, cool. All right, now we're gonna get into the nitty-gritty of factorial ANOVA, which gets a little more confusing. All right, so now let's pretend we didn't run the one-way ANOVA, and we had different ideas about what was going on with our data when it came to our empathy test. We have two independent variables, group and sex. And we think there might be something going on between these two, but we think that maybe, let's say, males and females are gonna differ when they're adults, but not when they're children or adolescents on this test. So that would be an interaction effect. So we'd set this up as a group by sex, which is a 3, because there's 3 levels, by 2, because there's 2 levels, ANOVA. You can switch that if you want and do sex by group, which would be a 2 by 3. It's the same thing. We have 6 different groups: male and female adults, male and female adolescents, and male and female children. So to do a 3 by 2 ANOVA, or any factorial ANOVA, which basically means more than one independent variable, we're gonna do the same setup as before. We're gonna go to Analyze, General Linear Model, and Univariate. This time, the only difference, we're bringing sex over here to the fixed factors. I'm gonna check post-hoc here, and I just wanna reiterate something that I think is super important. With these post-hoc tests, this is only good for main effect. So main effect would mean that there is an effective group that, irrespective of sex, the groups differ. Children, adolescents, adults differ. For post-hoc tests, you only need them if there's 3 or more levels. For sex, you wouldn't run a post-hoc test because there's only 2 levels. It's just like a t-test in that way. You can just compare the means to tell what the difference is. So I'm gonna leave just Tukey checked on this one. Press OK. And then this is all good. So we can press OK. And then it's gonna run our factorial ANOVA. So here we see the breakdown, how many children, 15, like we saw before, 23 males, 22 females. And then it gets a little more interesting because now we're looking at the interaction between these 2 variables, and we have 6 groups. So we have our male children, our female children, and then the same thing for the adolescents and adults. And what's great is that it breaks it down into their individual means, standard deviations, and then reports how many people are in these 6 different groups. So it kind of makes a good comparison that we can see between males and females in each of the different groups. So scrolling down, again, same thing, tested between subject effects is gonna have our F statistic. But this time we're looking at 3 things. We have potentially 2 main effects and an interaction effect. So a main effect, like I kind of said before, is that sex doesn't really matter right now. The groups are gonna differ, basically. So we're gonna have maybe adults having a significantly higher mean on the empathy test than children or adolescents. So we wanna see if we have a significant main effect. We're gonna scroll over. Here's our F statistic, 30.19, and it is significant at P is less than 0.001. So we have a significant main effect of group. Now we wanna look at sex. A main effect of sex would be, okay, we looked at group, doesn't matter, irrespective of group, we have a main effect of sex. And that could be, for example, kind of some of the things we saw Females are going to score significantly higher. They have a significantly higher mean score, basically, on the empathy test compared to males. So let's scroll over. F statistic is 9.28, and it's also significant at P is less than 0.01. Now, we have two significant main effects, but these aren't going to matter if we have a significant interaction effect. So a significant interaction effect basically says that one independent variable, its effect on the dependent variable, depends on this other independent variable. So it's a more complex analysis. We're saying that, for example, males and females differ only for adults, but not for children and adolescents. If we said that this was significant, but this wasn't, then males and females would differ across all three of the groups. But if this is significant, that might not be the case. So we want to check our interaction effect. We're going to scroll over. We have our S statistic at 4.41, and it's also significant at P is less than 0.05. So we know something richer is going on in the data. They depend on each other. So since we have a significant interaction effect, for these main effects, it'd be misleading to report them. So we're just going to go ahead and report the interaction effect. These don't really have the same richness or really accurately describe what's going on in the data like this does. So this post hoc test, for example, we don't even need to look at it. It's not important. Instead, we're going to do something called simple main effects, and that's how we kind of break down that interaction effect. So this is when syntax is going to come into play. With SPSS, you can do kind of crazy stuff like splitting the file, and it's like a multi-step thing. But I have a good cheat sheet that I got from a statistician at Cambridge. So I'm going to share that with you guys, and it's great. You just run these codes. You can change whatever the variables are right here, but you can keep everything else the same, and that will do your simple main effects for you. So we haven't kind of postulated which way we think it's going to go. So I have basically looking at sex differences within group and group differences within sex. So we're going to start with the sex differences within each of the groups. You're going to select this, press the green for run selection. Okay, so it's kind of populated our simple main effects. This is all the same stuff we saw before. So I'm just going to scroll down. Same here, and we're going to look right at the pairwise comparisons. So looking at sex differences within each group. Do male children and female children differ in their means on the empathy test? No, there is no significant difference here. What about for adolescents? Do males and females differ? Yes, there is a significant difference at P is less than 0.001. And because there's no negative here, we know that females have a significantly higher mean score on the empathy test than adolescent males. Adults, males and females do not differ. So actually, it was only in the adolescent group that there was a significant difference between males and females on the empathy test. Now that we kind of determine this kind of runs these one-way ANOVAs for us, but it takes into account the different interaction between sex and group. So we know that it's just in the adolescents group, and this is our F statistic. So we can just report that female adolescents had a significantly higher mean score on the empathy test than adolescent males, and then you can report the F statistic. So F parentheses 1,39 equals 16.71, comma, P is less than 0.001. And that answers that question for you of the sex differences within group. So that's one part of the interaction effect. Now, because we didn't really say either way what we thought was going to happen, I just want to see if there's any group differences within sex. So that means we're going to split into female and male and look at the different group differences just in females and just in males. So we have this code here. So you can see this one says compare by sex, looking at the sex differences, and this one says compare by group, looking at the group differences within sex. Okay, perfect. Scroll down to our pairwise comparisons. Now we're looking at males. So do male children differ in their performance on the empathy test compared to male adolescents? No, it is not less than 0.05. What about male children versus male adults? Yes, male children have significantly lower mean scores on the empathy test than male adults. You can tell the direction based on that sign, it's negative. And we have a significance value at p is less than 0.001. Now we go to the adolescent group. This is just the inverse of this, so we don't need to worry about it. We know it's not significant. Then we're going to look at male adolescents compared to male adults. Do these differ significantly? And the answer is yes. P is less than 0.001, and male adolescents have a significantly lower mean score than male adults. So just kind of to phrase it in an easier way that makes more sense, you can say male adults had a significantly higher mean score on the empathy test than male children and than male adolescents. Then we can scroll down, report our F statistic here, since it's kind of like a little one-way ANOVA that was compared. And you would say F parentheses 2,39 close parentheses equals 20.84, comma, P is less than 0.001. Perfect. Now our last comparison of the day, I promise, is going to be females. So we're looking at female children versus female adolescents. Do they differ? No. What about female children versus female adults? Do they differ? Yes. Significance value at P is less than 0.001, negative sign, so we know that female children had a significantly lower mean score than female adults. Now we can compare adolescents. Adolescents and children, we already know from here. Adolescents and adults, female adolescents had a significantly lower score. P is less than 0.01 than female adults here. And then last but not least, phrasing this in an easy way, female adults had a significantly higher mean score than female children and than female adolescents on the empathy test. And then last, you report your F statistic, which would be F parentheses 2,39 equals 13.23, comma, P is less than 0.001. And that's it. You're done. You just wrote down something so crazy, and now you have things that make sense to you. So you know there's sex differences within the group, you know there's group differences within sex, but really important when you have more complex hypotheses, when you're doing these factorial ANOVAs, that you really check into that interaction effect. Because if you were just to say that females had a higher score than males, it doesn't give you the same richness that breaking down this interaction does. Cool. Does anyone have any questions?
So good.
That was so clear.
You.
So helpful.
No worries.
So good.
Oh, thank you. I hope it was, it just took like so much of me teaching myself when I was doing my master's, that I'm glad that like I can break it down in the simplest terms, because it took me breaking it down in the simplest terms to understand it.
Yeah, interactions I feel like are one of the hardest things to conceptually understand.
Yeah, it's crazy. And like when you see the graphic representation, like they're gonna cross. So that's when you know they depend on each other. If you have two parallel lines, you know there's two effects going on, but because they're not crossing, they're independent of each other. So that would be like if you had two significant main effects, but your interaction wasn't significant, it would be the two parallel lines, because they're never gonna interact.
Yeah. Does the SPSS have a way to graph it, to look at it?
The interaction effect?
Yeah.
I'm not sure. I think so. Probably. Let's see. No. Well, let's try. Let me see if this would do anything. We did like a line.
Yeah.
Chart.
Oh, I think if you separate plots by, oh wait, no, that might not work.
Which?
If you separate lines by, yeah, do
This
one on the horizontal and then do one of your factors in the separate lines, I think.
Okay.
Does that work?
Yeah, let's see. Oh, yeah, there's the interaction effect. Perfect. Oh, great. Okay, awesome. So let's see what that looks like. Oh, that looks crazy.
Yeah, sometimes it can be a little easier to understand when you're looking at it, but I don't know. Well, kind of, yeah, you can see the main differences in the adolescent group.
Yeah.
And that adults seem to be higher overall.
Exactly. Yeah. So yeah, so if you want to graph it too, if that helps you, if you're more like a visual learner, then yeah, definitely do that. I mean, it gives you, SPSS does everything for you. That's why like I've always used it, because I'm not strong in coding and stuff like that. So this is just easy, like point and click. You just kind of have to teach yourself the basics of it, but it can pretty much do everything for you. Does anyone else have any questions or like anything I can explain a little more clearly?
I have questions, but I'll just message you after. Just like a lot.
Yeah, of course.
Yeah.
Okay. Well, great. Well, thank you for listening, guys, and I hope this was helpful. If anyone wants this syntax, like if they're thinking they're going to be running a factorial ANOVA for any project, just let me know, because like I said, you just change the variables here and everything else is the same, and it's just a one step versus multiple step to look at it like simple main effects for your interaction. But that's great. So thanks, guys. Appreciate it.
There's also an EM means in our package.
Oh yeah. Okay. Nice.
It does the same a little
I'm
bit.
gonna learn it. Don't worry. Like this is my like farewell to SPSS, and I'm gonna like transition to the next level.
It's good to know both.
Yeah, for sure. Great. Okay.
Oh,
Cool.
good, Chloe. Thank you so much.
You're so welcome.
So much.
Cool, right?
Yeah.
Yeah. Sorry, I only have like most like few people's faces. All right.
Yeah.
Sharing the screen. Okay. Great.
Awesome.
Thank you.